Hello everyone, welcome to Unacademy JEE English channel, and I'm here with Constraint Relation lecture number 2. And guys, I thought of doing live streaming, but due to some reasons I couldn't do the live streaming today. So I will try to do it as early as possible. Otherwise, I will upload the lecture in this form whenever it is not possible. So here in last class we have discussed about T.V applications, and today we are going to discuss rigid body constraint relations. So here you can say rigid body. First let's define the rigid body. A rigid body is said to be rigid if the shape of body remains same during the motion. That means the shape of the body is not going to change. The same thing we can say in other words also, that the distance between any 2 points doesn't change with time. So whatever way this body is moving, if we choose any two random points here, that distance is not going to change, and we will be using this property as a constraint, as a limitation to the problem. So distance AB is constant here. Now there are two type of constraints in rigid bodies also. One is isolated rigid body constraints. So suppose this situation is given, and for this rigid body any two random points we are taking which are separated by a distance of L, and we know that during the motion this distance L cannot change. So velocity of point A is given as v1 and velocity of point B is given as v2. So here you can see I can resolve this velocity component v1 cos theta 1, and this is v1 sin theta 1. Similarly here I can write v2 sin theta 2, and this component will become v2 cos theta 2. So now if this length is not changing, so velocity along the line joining these 2 points is going to be same. So this is one limitation which we are going to use in our problem solving. I hope this point is very much clear to you. So constraint wise we are going to get v1 cos theta 1 is equal to v2 cos theta 2. So this is here. Now if I observe with respect to this point, so this component I'll give in this direction. So omega of rigid body I can write v2 sin theta 2 plus v1 cos theta 1 divided by the distance between those 2 points. So this is how we will be calculating omega of this. Alright, and now sometimes rigid bodies are in contact. So if two rigid bodies are in contact, like here I have taken one rigid body and here I have taken one rigid body. So I have shown blue point and red point here. These are the points which are placed at the contact. Here I have drawn it slightly separately because so that we can comment on this, but they are exactly present at the same location where these two bodies are touching each other. So you can say here. So point P is lying on the body 1 and point Q is lying on the body 2. Now we can say even distance between them cannot change because P to Q also is rigid. So the previous logic we can apply in this situation also, that the rigid bodies, when they are touching each other, their velocities along the common normal must be same. This is common normal and this is common tangent to them. So along the common normal, this line joining point P and Q will become common normal, which is the same property as previous one. So these two logic we are going to use, and we'll be solving a lot of problems, and some really good problems I have come which I'll be giving you as a practice, and we'll be discussing them. So this is like a very common example you will see. So velocity of any one point is given, and for second we have to calculate here, right? So velocity of point B we have to calculate. So just resolve these two velocities. Method 1 I'm discussing, this is like very normal method. So here x and here it is y. So dx by dt is your v0 and minus dy by dt is your vb. So because x is decreasing and x is increasing and y is decreasing. Now I can write x square plus y square is equal to L square. If I differentiate this, I'll be getting vb is equal to x by y times v0. I'll be just substituting the values here. You can differentiate. I'm not explaining this part. So vb is equal to v0 cot theta. This is one equation. Now the same thing can be solved very easily if we use this constraint. Just see here. The component of v0 along the line joining A and B, because rod AB is rigid, which is v0 cos theta, and here if it is VB, this angle is 90 minus theta, so this will become VB sin theta. Now VB sin theta must be equal to v0 cos theta. So VB is equal to V naught cot theta we are going to get. Now the important part here is we cannot write AB is equal to A naught cot theta. We cannot write. The reason for this, because we have to differentiate this. So this will become AB, and that will come as first function into differential of second plus second function into differential of first one. So that is the reason, if the endpoints are having acceleration, in that case we cannot use AB is equal to A naught cot theta, because this term will come, and which is non-zero in this case. So this part you have to take care whenever angle theta is changing. You must take care of this. The same problem we were getting in T dot V method. That's why T dot V was always correct, but T dot A may or may not be correct. Alright. Now next example, the very simple one. In a sphere, one rod is placed and it is moving, this end is moving with V naught. We have to find the velocity of this. So let's see here, because we have to use circle geometry in this case. This is the normal here, and it will form a isosceles triangle here. So this angle is 90 degree. So this is 90 minus theta. Similarly here, if this is theta, this is 90 minus theta. So along the length of the rod, I can write this component as V naught sine theta, and this will become VB cos theta. VB sine theta, cos of 90 minus theta. So if I equate VA equal to VB, I am going to get. So this is the geometry in case of circle. Now since it is coming independent of theta, we can always say that AB is equal to A naught we are going to get. Next example we can take. There is a rod, and at the end of the rod there are two collars. Length of the rod is L. So at any given instant, this point B is moving this side with the VB, and at this instant this collar A is moving with the V naught. We have to calculate this velocity VB, and the collar B is moving on this rod, which is present at x equal to A in ZX plane, and this collar is moving along Y axis. Now here the thing is, solving this question using the velocity component, if somehow we can get this angle, we can directly write, or somehow we can find out angle here along this rod, we can equate the components, but that will not be a very good idea in my opinion. What we are going to do is, let's take at any given instant, this length is X, this length is Y, and this length is Z. So I can say here, length of X square plus Y square plus Z square in that situation is going to be L square. That is what we are going to do, and X value is A. So this relation we are going to get, and if I differentiate this, I'll be getting Y dy by dt and Z dz by dt. Dz by dt here I'm writing as VB, and dy by dt is minus of V naught. So if I substitute these values here, because I'm getting dz by dt is equal to minus y by z dy by dt. So minus dy by dt is V naught, dz by dt is VB, and y value we can calculate, y is y naught at the given instant. So z can be calculated using x square plus y square plus z square is equal to L square. Using that, z is known to. So now you know VB in terms of V naught, Y naught, and L naught. So I hope you have learned this example properly. Similarly here you can see, this is like very common question. So two rigid bodies are in contact. So either we can use along the normal, the velocity components must be same. So first method, or you can use geometry. So first I'm using that two rigid bodies in contact. So this velocity is V naught here, and its velocity component in this direction, because this is theta, so this is theta. So this velocity is V naught. So component in this direction will become V naught sine theta. Similarly, component of VR component of VR in this direction is going to be VR cos theta, and these two should be equal. So VR cos theta is equal to V naught sin theta, and we are going to get VR is equal to V naught tan theta. Now you have to take care of this theta. It is going to be a constant here. So if I differentiate also, if I differentiate at this moment, AR is equal to A naught I will be writing. If suppose this acceleration A naught is given and this acceleration AR is given, so this will be the relation here. AR is equal to A naught tan theta. This time we will not be differentiating like previous one because theta is fixed here. Similarly, method 2 you can use that the time in which this wedge is moving by a distance of x, in the same time this rod is falling by a distance of y. So here this triangle we can see this angle is theta, this is y, and this is x. So tan theta is y by x. Tan theta is y by x. So y is equal to x tan theta differentiated, theta is constant, we'll get the desired relations. One more time, if we'll differentiate, we'll get acceleration. The next problem here I can take, there is a sphere or a cylinder which is in contact with the wall, and there is a wedge here. So in this case, if a sphere has to maintain the contact with the wall as well as this wedge, then there is only one possibility. If you take care of these 2 points, wall is at rest, so sphere also should be at rest. That means along the normal, this velocity, because it has to make this contact, so only possibility this sphere will have is to move vertically down. This is what we are doing here. It is moving vertically down. This is V naught. So you can see here this is common normal. If this angle is theta, this angle is theta, here this angle is theta. So now along the common normal I have chosen these 2 points. So component of Vs in this direction is Vs cos theta, and component of V naught in this direction is V naught sin theta, and these two should be equal. Along the common normal we are taking, and let's equate them. So V naught sin theta is equal to Vs cos theta, so Vs is equal to V naught tan theta. Similarly here also we are going to get As is equal to A naught tan theta. The reason being, what is the reason for this? Theta is fixed here. Next, now this is very nice problem. At this particular instant I will make it masaledar. Let's check here. If this is having acceleration of A naught, okay, something is wrong. This acceleration is A naught here, and this is having acceleration of AR. All right. So there are again 2 methods. We can use geometry. Or we can use along the common normal, velocity components must be same. So let's discuss this. Here, these 2 points you choose, 1 point on the sphere, 1 point on the rod. So this rod is moving upward, so its velocity is VR, and we can choose this point here, and its velocity is in horizontal direction, that is V naught. Now along the common normal, these components are going to be VR cos theta, and this is going to be V naught sin theta. All right. So VR cos theta and V naught sin theta, these two must be equal. So we are getting VR is equal to V naught tan theta at this particular instant. But guys, you must see that theta is actually variable. If you'll see, this theta is actually variable. So next, when I'm going to write this, if I differentiate, so I'll be getting AR is equal to first function into differential of second plus second function into differential of first one. This is how this question will come, similar to the previous one, because theta was variable here. Now somehow we have to get the value of d theta by dt using this geometry, and if we get this d theta by dt, we can find out the relation between these two acceleration. Normally students will ignore this part. They will simply write AR is equal to A naught tan theta, and that's where they lose marks sometime. If the question has been designed in a way that where this term is significant, then you have to take care of, because in majority of the problem it will be just after release. So just after release means these velocities are taken to be zero in majority of the questions, but not here. So in this situation, let's calculate this d theta by dt. Seeing this geometry, they might give you the value of let's say this at any given instant this length is x and this is r. So basically we have to calculate, and this dx by dt only is x. Dx by dt is v naught for us. So if I write here, I'll be writing r sine theta is equal to x. Now I'll be differentiating it, r cos theta into d theta by dt, and this I'm going to get as v naught. So you can see here in these problems, this d theta by dt will be calculated either using geometry or by using diagram or omega. Directly we can write this. You can check here another way of solving it. We have to calculate. This is one way of solving it. I hope this is clear to you for d theta by dt. But normally smart students, how they will solve it, I'll just give the idea. If you see this part alone, you will find this omega is in this direction. Omega is in this direction, like this clockwise omega. So I can write component of velocity perpendicular to this. We have to find out this angle. Now this is v perpendicular. So omega I can write v perpendicular divided by that r. The distance between them is r. So this v perpendicular, from here we have to find out. This angle is theta. This is theta. 91 is theta. This angle is theta. So you can see here very easily we are getting v naught cos theta. I hope you are able to understand that there are multiple ways of calculating d theta by dt at this particular question. So that is what makes it very smart question, very difficult question also. Let's move to the next one. Now this is a question here. Here you can check. If you see this part clearly, there is a hinge rod, 4 hinge rod are given, and this velocity is given as v naught. We have to find out velocity of point A. Now point A will be moving this side and this will come down also, so its velocity will be somewhere in this direction. We can't say along the rod, but somewhere in that direction. Now there are multiple ways of solving this question actually. At any given instant, if this distance is x, this is also x by symmetry, so I can say d by dt of this entire distance is v naught. And if you check this part clearly, this is x, so velocity vx I can write as dx by dt, which is going to be v naught by 2. Now I have to calculate this vy. Then I can use rod constraint for this particular part, because this end is at rest and this end is having vy and vx. So I know if this point is at rest, this should also be at rest in this direction, because length cannot change. So if you see this part clearly, if this point is at rest, this is vy and this is vx. Component of vx in that direction is vx cos theta. Component of vy in this direction is vy sin theta. So these two must be equal in order to keep this length constant. Alright, so directly just equate it. Vy sin theta is equal to Vx cos theta. So Vy is equal to Vx cot theta. Vx we have calculated as V by 2. So velocity vector of point A, you are going to get V naught by 2 I cap plus V naught by 2 cot theta minus j cap. Let me tell you again here, if instead of V naught, A naught was given, then I hope you know that this part, if we are differentiating, we have to take theta also, similar to the previous problem. I'm not showing it here for acceleration. You can take it as a homework and you can try it. The next part is hinge rod, and a similar problem you solve in Crotov also. So my suggestion will be give it a try. There are 3 hinges in Crotov and ratio is 3 to 1. So hinge rods are given, multiple rods, and this is V naught here. So we have to find out velocity of point B, point C, and point D. I will use point C, maybe 1 point, and because the working is very similar in case of point C in the previous problem. So let's discuss here. This is 2L cos theta, 2L cos theta, L cos theta, L cos theta. So total is 6L cos theta. So d by dt of 6L cos theta is V naught. This is given to you in the problem. Velocity of point B, its distance from this reference, its distance from this fixed point is 4L cos theta. So velocity of B will be rate of change of 4L cos theta. So we already know for this 6 will come outside, 4 will come outside. So d by dt of L cos theta can be eliminated. So 4 times V naught by 6, 2 V naught by 3 we are going to get. We'll be getting 2 V naught by 3. Similarly for point C we can take. So we can use the previous logic for point C. See, this is exactly similar like previous problem. So I can write here its x velocity and y velocity component. Vx will become d by dt of 2L cos theta, because this distance is 2L cos theta. So d by dt of 2L cos theta I am writing. So 2 into V naught by 6, that will come as V naught by 3. So Vx for point C is going to be V naught by 3. Now to calculate Vy, we can just equate this x component and y component velocity along this line. So similar to previous problem, Vx cos theta is going to be Vy sin theta for point C. So from here we are going to get Vyc is equal to Vx of point C into cot theta. So this we are getting. This is going to be the velocity of point C. This is like a replica of previous problem. So I expect you should be able to solve, and please solve that Crotov problem, and do let me know in the comment section if you are able to solve that particular problem. I'm expecting majority of you will be able to solve. Let's take one more problem. 2 hinge rods are given here. 2 hinge rods are given here. Their velocity of point A is V naught, it is moving this side, and velocity of point B is 2 V naught this side. This angle is alpha and this angle is beta, and let's say at any given instant alpha and beta values are given as 30 and 60 respectively. So we have to calculate the velocity of hinge point O, which side it will be moving. Now it's very difficult to comment for us, so we will assume, since we are not sure, we will go with both x and y components. So I'm assuming here this is moving this side with Vx and this is moving downward with Vy, and this component is 2V naught and this component is V naught. Alright, so now we have 2 rods. Let's apply that rod constraint for this rod 1 and for rod 2. 2 equations, 2 unknowns we are going to get. So rod 1, if we take, you can see for rod 1, this is the rod 1. This velocity is V naught and angle is alpha here. This is Vy and this is Vx. Alright, so how much it will become? Let's write this. Component of Va along the length of the rod, that is V naught cos alpha. Component of Vx along the length of the rod, that is Vx sin alpha. Component of Vy along the length of the rod, that is Vy cos alpha. So let's equate the directions first. Both are, I'm taking one side. Now I have to equate magnitude. So V naught cos alpha is equal to Vx sin alpha plus Vy cos alpha. If I equate, this is my equation number 1. Similarly, I can take this rod 2, and you can see this is the rod 2, and this end is moving this side with the velocity of 2V naught, and this angle is beta. This horizontal component is Vx and this is Vy. So I can write along the line joining 2V naught cos beta is equal to Vx cos beta here, Vx cos beta, and this is also having same direction, by the way. This is also having same direction. So component of Vx in this direction is Vx cos beta, Vy sin beta, and that must be equal to 2V naught cos beta. So 2V naught cos beta is equal to Vx cos beta plus Vy sin beta. Here plus sign should come. Alright, now we can simplify and we can get the value of Vx and Vy. That part I am not solving. You can substitute values and you can solve. And finally, this is how I am going to report the answer. One more problem we can take on this constraint relation. Let's say there is a cylinder which is trapped between two wedges having angle of inclination 30. They are identical, and this is moving this side with 2v0 and this is moving this side with v0. We have to calculate velocity of cylinder Vc. Alright, so again I'm not sure which side the cylinder will move, so I will take Vy and Vx, these two components. I will apply when two rigid bodies are in contact, their velocities along the common normal are going to be same. So let's see, this is one normal, this is one normal. Unknown is Vy and Vx, two equations, two unknowns. So let's check here. This is the contact 1 and this is the contact 2. So along the common normal, velocities we have to equate. So if we see this contact 2, directly I can see Vx is 2v0. Contact 1, if these two bodies have to be in contact, Vx is going to be 2v0. Directly I can say, I'm just showing it here. Now contact 2, if we take, this is how this situation will be. And similar to those rod problems, just treat this as rod and you will say, oh sir, this is exactly like previous problem. Imagine here to here is a rigid rod, because this length cannot change. So same thing we have done in the previous problem, which we are going to do it now again. So this will be V0 this side, because this wedge, all the points on the wedge will be having same velocity. And this is Vy and this is Vx. So Vy sine 60 is equal to Vy cos 60 and minus Vx cos 30. V0 cos 30 or sine 60, anything you can write. Vy cos 60 and Vx cos 30. So net, first equate the magnitudes and equate the magnitudes also. After that, I'm not solving it. I hope you will get the answer for this. All right. Similarly, this problem we can see angle theta is constant. So here V0 and this will be moving down with VR. So just equate velocity components along the common normal. So this is V0 and this is VR. So VR cos theta should be equal to V0 sin theta. VR cos theta should be equal to V0 sin theta. So VR is equal to V0 tan theta. Directly we can write. I think you will be getting a better idea how exactly this constraint works, and we have done sufficient number of problems. So today you give it a try from all the books which you find, and give it a try for these constraint relations. I will include few more problems, and if needed, just let me know in the comment section that if you need more practice or more classes on that particular topic, because I'm going with some idea like, okay, these many lectures I can finish, but if you feel you need more, you can always tell in the comments. Now, important note here, you can see the rigid body constraints are valid only for velocity and not for acceleration. That is very, very important point. However, acceleration relations can be obtained by differentiating the velocity relation. See, this is where normally students make mistake, because they become habitual of writing that velocity along the common normal is same, so acceleration along the common normal will be same. That is not the case always. I have shown you whenever angle theta is varying. And this is another example here. Suppose point P is given, and you can see along the line joining, their velocity components are 0, 0, which are equal. But if you see acceleration, this is having x1 omega square and this is having x2 omega square. So you can see they will never approach each other, but still they are having different accelerations. So acceleration condition will never apply in in case of finding relation. We'll get the velocity and we will differentiate it. That is what is all about constraint relations. So I'm going to give some practice problems. Just these are easy problems. I'm sure all of you will get. This is problem number 1. This is problem number 2, problem number 3, problem number 4, and this problem number 5. This is 6. All these are from the book of Mr. Rahul Sardana. So it has very good problems. So if you want, you can use that book also. This problem number 7, 8, 9, and this 10, 11. So some very nice problems are present. 12, I think 13, and this 14. So more are there. So problem number 15. So these are the problems, and give it a try, practice these problems, and we will be discussing them. If require, I will discuss. Otherwise, if you are able to solve, that's fine. And that's it, guys, in this video. Practice constraints properly, and I'll be coming up with more lectures, and definitely we will be doing live streaming very shortly, right? So thanks for watching it. Please subscribe this channel, it's a request, and share this channel with all your friends. It will be a great help. Thank you.